but they're not. And we work on dwarf galaxies, and I think most of the things that we present us will be on this. And recently moved to Bonn, to a newly opened department of the Max Planck Institute for Radio Astronomy, led by Amélie Saint-Onge, to work again on the baryon cycle of galaxies, JWST, etc., etc. So I give the floor to him.
So, hello everyone, thank you for the very kind introduction and the invitation here. So today in this seminar, I will tell you about some recent results on the baryon cycle of galaxies, specifically focus on feedback from galactic outflows. And you can see here some of the main collaborators I'm currently working with. So I've been using this background image for a lot of talks now, but the reason why is that this is a very nice example of feedback acting in the local universe. And okay, so if we look into more details, this is a composite image of MET2, which is a nearby star-forming galaxy. And here you can see in blue, in this bluish light, the stellar disk of the galaxy, and in red, this biconical outflow that is extending perpendicularly to the stellar disk, that is showing how the ionized gas from H-alpha emission is spreading out the interstellar medium up to reaching the circumgalactic medium of this galaxy. And here you can see a more schematic view of galaxy evolution. We know that galaxy evolution is ruled by the baryon cycle that basically describes the interplay between all the processes involved in the gas, the dust, and the star formation within the galaxy. So we can say that this cycle starts when the gas cools down into molecular clouds, allowing the formation of new stars. And then these stars evolve, producing stellar winds and exploding as supernovae, and enriching the interstellar medium with processed elements and dust. And both the star formation activity and black hole activity can actually produce very strong winds, resulting in large-scale outflow that can hit and push the gas outside of the interstellar medium, eventually stopping the formation of new stars. And you can see that depending on the outflow velocity, this material can just fall back into the galactic disk where it can still be reused for future star formation, but it can also enrich the circumgalactic or even intergalactic medium. And after that, the cycle starts again by accreting new fresh gas from the intergalactic medium or via major mergers, for instance. So among all these processes, as anticipated before, I'm mostly interested in feedback from galactic outflows. Therefore, during the seminar, I will mostly focus on that. So first of all, why feedback is important in galaxy evolution? We know that feedback is a key ingredient of all theoretical models and cosmological simulations because it is needed to reproduce the observations of galaxies as a function of time. And for instance, here you can see the luminosity function of local galaxies, as shown by these black points. And in this figure, the stellar mass increases from the left to the right. So here the dashed line represents the dark matter halo mass function, and all the other lines are different models based on star formation suppression mechanisms in these galaxies. And as you can see, all these models basically fail in reproducing the observations, over-predicting the number of faint and bright galaxies with a shallower slope as compared to the observed ones. However, when including feedback, the models tend to be much more in agreement with the observations, and in particular, we can recover the faint end of the luminosity function by including supernova feedback for galactic fountain mechanisms, while at the higher mass end, we need some stronger feedback that usually is driven by AGNs. And feedback is also needed to reproduce some observational scaling relations between different galaxy parameters. For instance, on the left, you can see the well-known black hole mass sigma relation that can be partially explained by the presence of AGN-driven winds, while on the right, there's the mass metallicity relation whose bending at the lower stellar masses can be partially also explained by stellar-driven outflows. And another way to show the need for feedback in galaxy evolution is by studying diagnostic diagrams that are based on observational properties of galaxies. This particular one is called dust formation rate diagram that is showing the specific mass of dust as a function of specific star formation rate for local dwarf galaxies and high-Z galaxies. And this can be seen as an evolutionary diagram in which galaxies start building their dust grains at very high specific star formation rate or young ages. And then this dust can be destroyed or removed via star formation or outflow at older ages. And these solid lines represent different tracks from chemical evolution models attempting to reproduce this dust cycle in these galaxies. And these models basically take into account some chemical composition of the galaxies and their evolution as a function of time. And in particular, they take in input parameters like the initial mass of gas, the star formation history, the initial mass function, but also the presence of inflows and outflows. And the outflow efficiency usually is described through this parameter that is called mass loading factor. That is the ratio between the outflow rate and the star formation rate of the galaxy. So when this quantity is much greater than 1, it means that the outflow is much more efficient as compared to the star formation in depleting the gas and the dust from the interstellar medium of galaxies. And as you can see from here, these models are largely dependent on the outflow efficiency, and in particular, the models with low mass loading factor, like these purple or gray lines, are too flat in order to reproduce the observational data. And also the models predict values for the outflow efficiency that span almost orders of magnitude. So from this picture, it's clear that we really need some observational constraint on galactic feedback in order to remove some degeneracies in the models and to better describe the baryon cycle in galaxies. So first of all, in order to observe galactic outflows, we must say that outflows are multi-phase. That means that they can drag different phases from the interstellar medium, including the ionized, molecular, and atomic phases. And all these phases can contribute in a different way to the outflow mass and energy budget. For instance, from this figure, you can see that for local galaxies, the molecular and the neutral phase account for the majority of the mass outflow rate. And of course, different phases also imply different conditions from the galaxy, so different temperature and density. That means that we also need different methods in order to get the complete information from these galactic outflows. And among the different methods, for instance, we can measure the blue shift or rest frame UV absorption lines as compared to the systemic velocity of galaxies that is very sensitive to the efficiency of the outflow. But we can also study the emission line profile of optical or far-infrared lines by looking at the broad wings at high velocity in the spectra, or we can use spatial information. For instance, we can decompose the galaxy in a disk and the outflow component and study their morphology and kinematics. And of course, we also must choose our targets in a careful way because we want to extract as much information as possible from the outflows. And we know that dwarf galaxies are really interesting candidates in this respect because they are much more affected by outflows as compared to higher mass galaxies. And especially in the local universe, they can offer a unique opportunity to study these phenomena in great details. Another point in favor of dwarf galaxies is that they are thought to be analogs of high-Z sources because they share similar properties in terms of star formation efficiency, size, and metallicity. So they can also offer the chance to provide some insights in galactic feedback in more distant galaxies in the primordial universe. So because of that, we decided to conduct a search for galactic outflows in a very well-studied sample of local dwarf galaxies from the Dwarf Galactic Survey, or DGS. These galaxies this is a sample of 48 dwarf galaxies observed in the far-infrared with Herschel, and you can see them here at 70 micron emission. And these are nearby galaxies, so they are at distances smaller than 200 megaparsec. They are characterized by subsorbed metallicity, and they also benefit from multiple spectroscopic and photometric information. So we started searching for outflow signatures in these galaxies by looking at the C2 line at 158 micron, because this is one of the strongest lines in the far-infrared regime of the galaxies. It was also observed for all the galaxies in our sample. And it was already used to detect galactic outflows both in the local and high Z universe. And so we selected a subsample of 29 galaxies for which the C2 emission was completely covered by the Herschel spectrograph, and with good signal to noise in C2 emission in order to study their spectral emission. So you can see the distribution of our galaxy in the star formation rate stellar mass diagram. Basically, all our galaxies lie along the main sequence that is represented by this solid and dotted line, with some of the galaxies tending towards the star-bus-dominated region. And so to analyze galactic outflows, we fit each C2 line with a single and double Gaussian profile, with the latter including both a narrow and broad component, and also by inspecting the corresponding residuals. In some cases like this one, you can see the presence of the outflowing gas from the high velocity wings of the spectrum that cannot really be constrained with a single Gaussian function. But when including a broad component, it clearly matches the high velocity wings, improving the fit. And so we found that 1/3 of the sample was showing clear signatures of outflowing gas, while for the other galaxies, if the outflow was present, it was too faint to be individually detected. And from each spectrum, we derived different quantities. In particular, from the broad component, we estimated all the quantities of the outflows, including the outflow velocity, size, and mass. And we use this information to compute the outflow rate, that is one of the key ingredients of the mass loading factor. And in this figure, we compare the outflow rate with the star formation rate of the galaxies. And the circles here are the individual outflow detections, while all the squares are just some results from a stacking of the sample. And here, everything is color-coded by the mass loading factor. So as you can see, our galaxies lie along the one-to-one relation in between the observed relation of local star-forming galaxies and AGNs. And this implies mass loading factor of about 1 that, if you remember, are much lower than what predicted by chemical evolution models. The discrepancy between the model and the observations can be partially explained by the fact that we are only looking at the atomic phase in the interstellar medium, while in principle, we should also account for the ionized molecular phase. And just yesterday, we got this fresh news that we will get some hours of observations with APEX to get C1 emission in some of these dwarf galaxies. So ideally, we will be able to characterize a little bit more the outflow from the molecular phase, assuming that C1 is tracing the molecular gas in these galaxies. So we studied the CGM-IGM enrichment, possibly due to the outflows in our galaxies, by estimating the escape velocities, that are the velocities required by the gas and the dust to escape out of the dark matter potential of our galaxies. And we compare them here with the outflow velocities. So again, in the plot, all the circles represent the individual outflow detections, and all the other symbols are local star bars or dwarf galaxies from the literature. And everything is color-coded by the stellar mass. So you can see again that our galaxies lie along or above the one-to-one relation, suggesting that the outflows can really push the gas outside of the interstellar medium, enriching the intergalactic medium. And to quantify these, we estimated the escape fraction of the galaxies that are defined as the fraction of the outflowing gas with velocity larger than the escape velocity. And we found on average that 40% of this gas can actually escape into the IGM. So here it's also interesting to note that the galaxies with the lower stellar masses and metallicities are also those with the largest escape fractions that are represented by this bigger circle in the figure, possibly suggesting that these galaxies are actually shaping the low mass end of the mass metallicity relation. But for this, actually, we need more statistics in order to really investigate this kind of aspect. We went a little bit farther into this by extracting also spatial information, average spatial information from the gas, dust, and stellar continuum in our galaxies by stacking their C2 far infrared and ultraviolet emission, and extracting also the corresponding radial profiles. So as you can see from here, the average gas and dust emission are actually more extended than the stellar continuum. And to quantify these, we fitted all these profiles with a single and double Sirsic function. And we found that a double Sirsic is actually needed for all the components, especially to match the profile in the largest radii. But a broad Sirsic function is more prominent for the dust and the gas as compared to the stellar continuum. So this is a further indication that we have some gas and dust that are more extended than the stellar disk, possibly due to the outflows. And we also compare our measurements with those from high redshift star-forming galaxies observed with ALMA, for which we have some indication of C2 extended emission possibly due to outflows. And we found actually that the spatial extent of our galaxies is similar to what is observed also in the primordial universe. That can be an indication of some common mechanism at the origin of this extended emission. At the same time, we also know that at IZ, the situation is much more complicated because we do not have enough resolution to really disentangle all the processes that can provide this kind of extended emission. Because apart from outflows, we can also have some small clumps of satellites that can be maybe unresolved by current observations, or the fact that two galaxies can interact with each other can also provide this kind of extended emission. So for sure, more investigation is needed into this kind of problem. And following this open problem at IZ, I will just provide some results also about the baryon cycle for, let's say, the high redshift universe. So as I said, we know that the primordial universe is much more different from the local universe because we know that the ISM of galaxies were much more chaotic, that the merger rate was much higher, so galaxies were more prone to interact with each other. But at the same time, as I said, primordial galaxies share some similarities to local dwarf galaxies. So it is actually needed to investigate the link between the primordial and the current star formation. And this is why I'm showing you this plot. This is a very known plot that is basically the cosmic star formation rate density as a function of redshift that represents the star formation history of the universe. And here you can recognize three different epochs of cosmic activity. So going from an increase of the star formation rate density from very high Z up to redshift 3, then there's a peak around the cosmic noon, and again a decrease towards the local universe. However, this picture has significantly changed during the last years, thanks to new observation in the restrained far infrared that started populating this region of the cosmic star formation rate density that was previously quite unsampled. And we know that there are now many programs that are currently investigating this problem at IZ. And among them, there is also the ALMA large program Alpine that most of you probably know already. But just as a reminder, Alpine is the ALMA large program to investigate C2 at early times. This was a survey conducted some years ago now that observed the C2 and dust continuum for a sample of hundreds of normal star-forming galaxies at high redshift between redshift 4.4 and 6, and in galaxies along the main sequence, so with star formation rate from 10 to hundreds of solar masses per year and stellar masses between 10 to the 9, 10 to the 11 solar masses. And just as a reference, this is how these galaxies look like in situ emission. You can see they are very different from each other. They have different sizes, morphology, and kinematics as well. So using this data, we started investigating some aspects of the baryon cycle in these galaxies. And in particular, here you can see again the dust formation rate diagram that I showed you before for the local dwarf galaxies, but this time for the Alpine galaxies color-coded by the stellar age. And this is how this diagram looked like when we run our chemical evolution models onto these galaxies. So here, what you are looking at is different sources of dust production including supernova type 1a, type 2, the AGB stars, supernova type 2, and also the presence of dust brought into the interstellar medium. And here the models range from a maximal dust formation without including any feedback to a minimal dust formation, but with the inclusion of feedback. And what you can see is that models are currently reproducing, especially the older galaxies, but they are not able, they fail basically in reproducing the dust amount in the younger galaxies. And so we investigated this by taking into account a possible different shape of the initial mass function. So you can see here in this sketch, like the shape of a canonical Chabrier IMF. And for this galaxy, we decided to investigate the impact of a top-heavy IMF. What does it mean? It means that in this case, we are basically producing more short-lived massive stars that can evolve much faster than in the case of a Chabrier IMF, enriching in a quicker way the interstellar medium with heavy elements and also dust. And so what happens is that the data basically shift to older ages, and also the models shift towards larger specific dust masses. So by using a top-heavy IMF, we actually managed to recover most of the galaxies, but at the same time, we still miss these kind of younger galaxies for which we have a very large and quick dust production. So we are currently investigating this thanks to new joint observations between ALMA and JWST. And in particular, we have now information from ALMA that is giving us information on the gas and dust properties of the galaxies, but also we have JWST that is providing much more information on the rest frame optical regime. And for these galaxies, so we have new NIRCam observations that are giving us higher resolution in the stellar part, but also NIRSpec that is covering some of the most prominent optical lines, including H-alpha and oxygen 3. And with these lines, we can currently also study some properties of the outflows in these galaxies from the ionized phase that was not previously possible. And this is what we are actually doing with a master student at the Max Planck regarding galaxy mergers. So we are selecting galaxy mergers from ALMA, as observed from ALMA, and we are also adding this information from JWST. So for instance, here you can see one of the galaxies in our sample. This is an RGB image made with NIRCam filters, and you can see in orange the previous ALMA contours of C2 emission that shows this extended emission between the two components. But now we can also see how the ionized gas is also extended between these two components, also forming this ridge of gas. And the idea, this is very preliminary, but the idea is just to select, to get, let's say, spectral information from different parts of the galaxies or the system and see if there is any evidence for outflowing gas in the H-alpha or oxygen 3 lines that is possibly can be seen through these kind of extended components in the spectrum. So this was my last slide. I possibly can leave you with the take-home messages, and yeah, I'm happy to take any question.
Thank you very much for this perfect time. Question? Fabi?
So if we go back to the specific dust mass versus specific stuff pressure. So you say that the model which is basically the dashed black line, right, reproduces well the low specific stuff formation rate part and less well the guy. But it seems to me that also in the lower part of the specific stuff formation rate axis you have problems.
Yeah, actually, I think it's a problem of how it is plotted, in the sense that these are the individual components, so the different colored regions, while this black dashed region is just the sum of them. So basically, we can reproduce these galaxies here thanks to supernova type 2, but yeah, it's just a matter of plotting probably, because these solid lines is just the sum of these components, so it's still including those components.
Yeah, but I mean,
From
you
the
should look at the
no.
sum of everything, right?
Sorry?
You should look at the sum of.
Yeah,
of
yeah,
them.
yeah,
So
yeah.
you should look at, you should compare the dashed black stripe versus the point, and you overshoot the point.
No, but yeah, I got what you are saying, but actually, this is not really the minimum of this. It just, how to explain? So what I want to say is that the sum of the minima of each component is actually taking this into account as well. So it is covering, but yeah, it's probably a bad plot. But it is covering these points here, yeah. The problem is only for these ones.
Please, question.
Thank you for the talk. And like still in this plot, I mean, you consider, like you said that basically the line, not dash, but the total dust is just the sum of the components. So, but you consider also like the destruction by supernovae.
Yes.
And the other question about this, it's about the variation, you know, about in the supernovae type 2 yields that are extremely uncertain, like which range. Try to.
Yeah, I don't have this on top of my head.
Okay.
I can tell you because we have it in the paper. Yes, basically this includes that uncertainty as well and the uncertainty on the condensation fraction and so on.
Yeah.
Yeah, but I can tell you about the numbers.
Last question from Francesca.
Okay. Thanks, Michael. In this plot, galaxy, we are considered as single sources,
Yes.
but you prove that at the end of your seminar that some are pairs, some of them are not.
Yes. Yes.
So it's possible that some of the galaxies that do not that are not reproduced by the model. I mean, there is a trend.
So here we included everything. We included also mergers in the sample, but we saw that mergers are basically distributed everywhere. So we are considering only the main component of the merger so far, but it looks not to be very concentrated in this part of the plot. So they are distributed everywhere. What we can do next actually is to improve also the modeling is to consider different components like individually and see if they just.
Now we just consider
the central major component that was the alpine target, and all the rest is not.
Okay, so let's start the speaker again. And let's move to the second talk. Just one quick change.
I can
Yes, you can. Michael, can you stop sharing them? Or
It's already there.
Okay.
They're ready.
It's okay? Yeah, that's fine. Perfect. Okay, this is the pointer. Yes, and that's it.
Yeah.
I will give you 5 minutes before the end.
Okay.
Please.
Okay, so this is the second talk of today, and the talk is given by Nijé Jean. Nijé is presently at the Stockholm University at the Department of Astronomy, working on Foremost. Foremost is a survey that is going to start very soon from the Southern Hemisphere. Today, but before that, Nijé did his undergraduate studies at the Normal University in Beijing, then moved to Tokyo for the PhD, where he took his PhD 2 years ago. And he's an expert on stellar spectroscopy, high resolution stellar spectroscopy, and is working in Foremost exactly on the pipelines for the reduction of galactic archaeology, of the galactic archaeology part. So we hope that something will come out from that. But today, Nijé will be presenting something based on other measurements, other spectra, other information on hot stars. And thank you.
Thank you, Angela, for that. I can restart my timer. Yes, so my expertise basically lies on stellar spectroscopies, but this is not what I'm going to talk about today. We are more on something like the massive stars, etc., etc. So this is a kind of small side project I with my undergrad supervisor Noriyuki Matsunaga, I found out very interesting when I was still in Tokyo, something like that. Yeah. So massive stars. Massive stars, a star. Basically, if we know that all stars rotate, right? So this is the main topic of, yeah, okay, I can flip it. So all star rotates, especially massive stars. If we go from something like the sun to Altair to more massive stars, we can see that the rotation speed of stars increases, right? So the physics is very simple in here. So basically, if your rotating velocity increase, it basically means that your stars start from something like a sphere to an elongated shape. It's one of the phenomena when you rotate yourself very fast. The second one, if your stars rotates really fast, the materials in the equator of the star may be ejected from the material and then form a disk. And this is what we call the decretion disk of massive stars. Yeah, so this is the physics, all the physics in here, right? So this is kind of simple and easy. I need to remove this one. Okay, yes. So our main topic is actually in this decretion disk, and I compare it with something we are more familiar with, which is the accretion disk, right? But they are not the same thing, because accretion disk, the materials are like drop into the surface of the star. But for the decretion disk we are talking about here, the materials is actually ejected from the surface of the star. So they have different orientations. So, but however, like, although these two things are different, but they are also the disk. So, what I'm showing here is that we can see the, we can see the effect of the disk, whether they are accretion disk or decretion disk. So they are basically the same. So I borrowed a figure from the accretion disk, right? So if we have a star with a disk, then of course the star. So the combination of these two things will be brighter because we have a star and we have a disk. There are some radiations from the disk, right? Also, the color of the whole thing, the star plus disk, will be redder because mostly the disk emit light in the infrared, not in the optical. And the third thing is that yes, so the disk will show some kind of H alpha emission. So this is the difference between when you have a star alone or when you have a star with a disk together. So going back to the decretion disk phenomena here, this is the point that we are interested in. Why want to studying this phenomena is that this disk is not permanent. It's unlike accretion disk will basically last for maybe millions of years after the star was born. The time scale of this kind of decretion disk is only years. Yeah, so we can now describe the decretion disk by what we call the viscous decretion disk theory. So we have theory on the prediction of if you have a star with a disk, what it should look like. So the creation and dissipation of the decretion disk is what we call the BE phenomenon. So that so our B-type star become the emission line B-type stars or going back. So this is the same thing. Okay, so we can see here that this is what the theory tells us, that if we have a star, then if you have a star on t equals to 8.0, something like that, and it's only a star, then we start the event of decretion. So for some reason, we don't know why, but the star develop a decretion disk after a while. So you can see that in the optical stars, depends on the viewing angle of our observer, the star can be a bit brighter, not changing brightness, or become fainter. And after the accretion event ends, it gradually decrease or increase back to the magnitude of the initial one, right? So this is easy. However, if we look at this in the infrared, we will see something different, because as I just said, the main radiation of the disk is actually in the infrared. So whether we are face on, middle side, or edge on, basically all the magnitudes or the brightness of the stars actually increase during the BE phenomenon, right? So this is the main difference between the BE phenomenon in optical and the infrared. And as I just said, we are not so sure why this happens, and because I'm not the one doing the model of the star, so I'm thinking that, okay, can we detect more BE phenomenon in the infrared? Yeah, because one of the bottleneck for studying this event is that we don't have so much observation data to have this BE phenomenon, since the time scale is years, and we usually don't have such a survey in the infrared, which lasts for such a long-term survey. Right? So we don't spend millions of euros to just look at one star for 2 or 3 years, right? But luckily, we do have something like this. So we have the WISE, the Wide Field Infrared Survey Explorer, which works on 3.4 and 4.6 microns just in the infrared region. So this is good for detecting the BE phenomena. It will be easier because it works in the infrared, right? Yeah, so it launched on 2009, and the observation started on 2010. The observation of WISE is actually quite in an interesting way, is that it basically measured the same small area of the sky in 2 days, basically 15 epoch, and then it goes to the other side of the other part of the sky and the other parts, and after half a year, it goes to this same area of sky again. So we can get again like around 15 epochs after half a year, and these things repeat and repeat and repeated. Of course, the observation paused for a while after 2011, and then it resumed as a new WISE project basically until now. So the time scale is actually quite long, and it's good for detecting the BE phenomena in the infrared. That's good, right? So basically half a year ago, I was saying that this game we can play forever because WISE just observing there. But it's quite unfortunate that I think the orbit of WISE is now too low, and I think it will go back into the Earth this year. So we cannot play this forever. But anyway, starting from 2010 until 2025, we have a baseline of more than 10 years. Actually 16 or 17 plus observation for all the stars in the sky. That's good, right? Because I've said this, because we can use it as a time series data, for example, to study something like a very short time scale for detecting surface settings or outliers, like the what Changjiao done in 2018, or we can look at some long-term variability of some stars, like what Yang Ming did in 2019. So this is the observation or the time series data of the WISE, W1 and W2. So this is very good, because if we bin all the photometry of one scan in here, around 1.5 days, then we have a time scale of more than 10 years, which is very perfect for detecting more BE phenomena in the infrared. Right? So we have the data, we have the theory. The next step, what I do is just, well, let's grab all the BE, the non-BE stars to verify if we can do this in WISE. Right? So this is something like 3,000 classical BE stars. We know they have emission line, so they should show something in the WISE photometry. And then we extend it to a larger sample, which is back then was all the OVA stars in the Milky Way confirmed by spectroscopic survey from Apogee, Lemos, and Gaia ESO, etc., etc. So we have a larger sample, and we want to see if we can find some new BE stars, not from the spectroscopic, but using photometry. Okay, this is the last piece of the evidence, last piece of things I want to talk about before I show the result. It's also good that, I don't know why, but it dated back to my 2017 paper about, and 2020 from Deng Shan, that the intrinsic color of the OBA stars in the infrared is basically always minus 0.05. So if we see a OBA stars have a color rather than minus 0.05, we know that they should have a disk around. So this is good, right? So if we plot all the stars from the golden sample from all epochs observed by WISE, so we have the color W1 minus W2. There's no zero here, sorry, I should remove that. Versus W1 here, we see that most of the stars actually lies on the colors of minus 0.05 around it, right? So this is good. But we also found that a large portion of the observed points are actually redder than minus 0.05. So it's good. So we can say that we have detected this B phenomenon in the wide bands. Yeah, so this is what we aim for and what we should look at it a bit. Okay, and then things become quite easy. This is just some details of like how I select all the stars in this region, just like the error, measurement error here is too large, here is too large, we don't like it, and we just grab all the points in here and find and look at what are they simply, right? Okay, but the things is not so simple. We found how many? Sorry, did I say how many? No. And we found around 1,300 stars in this region. However, as I said, stars becoming redder and brighter is actually the most classic characteristic of BE phenomena. But for those 1,300 stars, they are not always true. So we have half of them, more or less, which is good. So when the star becoming brighter, it also becomes redder in the W1 minus W2 colors. That's good. But we still have some more stars which is have some changes in the brightness, but the color is more or less the same. So I grouped it as group 1 and group 2, and we are limit ourselves into this group of stars in here. Right. So it's good, but we still need to find a way to classify these stars to group 1 and group 2 automatically, because we have 20,000 stars. Eventually, I don't want to look at the light curves one by one. That's too much, right? Eventually, we found that there is an anti-correlation between the color and the brightness of the star, because B phenomena is something like that. It becomes redder when brighter, so it always goes up like this way. So we found that if we plot all the points in here, then if the Pearson correlation coefficient is like less than minus 0.74, then it's a good classification between group 1 and group 2 stars. Right? So using that classification, we can finally have 500 stars in the golden sample and 402 more stars in the extended sample in the OBA stars. So eventually we have around a bit less than 1,000 BT stars. So by seeing T here means that in the last 10 years, this B-type stars changes from B-type to BE type, or change from BE type back to B-type. So we don't have the ability to detect much BT stars before, right? But we can do it in the WISE photometry. Yeah, so, and in the same time, if you look at the color magnetic diagram of all these stars, we can find that the distribution area of these points are actually quite correlated with what the models predict to us. So this is all the models' prediction of B-type stars turn to BE-type stars, how the color and brightness would change, or vice versa. Yeah. So this is also very good, very good consistency what we have achieved. Right? Okay. What else? Here I show some of the light curves we have. The Dominican 2002 review paper say that the light curve of BE star will have some sharp and hump-like shape in the light curve. We are basically more biased to this shape because our separation between observation points are half a year, so we cannot detect short time scale variations, right? So we have something like this, one BE phenomena, very good. we have some multiple, like maybe quasi-periodic change in brightness, very short time scales, and again, we decrease from a disk phase and then go a bit up again and go back to the normal phase of it. So this is good. Yeah, so, okay, 10 minutes, good. One important question we need to ask ourselves is that if we want to model the whole period of the BE phenomena, how long we should monitor for a single star, right? So here for each of the light curves, I actually classify the different period into what I call the outburst period, because the brightness goes up, and decay period because it goes down and goes up again and goes down again. If we do it for all the stars I found and plot the histogram of the time span of the outburst and decay, and then we found that the median, so most of stars, the outburst events last for around 500 days, and for the decay phase, it also lasts for around 500 days, but the decay phase seems to be a bit longer than the outburst phase. That's also kind of easy, right? Easy to say. Okay. And if you still wonder this, if you still wonder if we can tell this is really the disk event or not, this is the final evidence I can show, is that we can combine the spectroscopic observation from Lamos to all these stars. So because Lamos medium resolution now have some time series observation. So for example, for these stars, we have 1, 2, and 3 Lamos observation for the H alpha line. Then we can see that for this observation and this observation, they are in absorption. But for the one which have a W1 minus W2 rather than minus 0.05, is clearly that this absorption change into emission line. So this is basically definitely saying that it is a disk event, right? We can even see something like that. The color of the star actually is correlated to the amount of emission. So showing different extents of the disk, right? Yeah. We also try to correlate the amount of emission with the color. Again, they should have a negative correlation. That's true, and this is also so we can see that when the OBA stars become redder than minus 0.05, basically we always get a emission in the H alpha line. Again, disk event, and the distribution of the points in this line is also consistent with what the models tell us by these lines here. So this is also good. Yes, we can also derive some of the parameters in here, because like the rho actually increase according to the model, but the n here actually increase in this side. So if you have a stars in here or in here, the disk, the physical property of the disk may be a bit different, and we may can tell something from the WISE photometry in here. I will skip this. So, but the point is that this kind of stars will tend to appear in more younger clusters, not older clusters, because for older clusters we don't have OBA stars. That's also true. Okay. I will skip this point, but recently what we have done is that instead of, did I show? Oh, I didn't show that. Oh no, okay. Previously, we only used the data from the northern sky, so which our sample is limited in the northern sky, but now we actually extended our sample using the Gaia OBA stars. So we have actually more, the larger number of B stars in here. Okay, I'll skip all these things. One interesting question is the last 2 slides. It's only 19 minutes. Okay, it's good. One interesting sample we can ask a bit ourselves is that there were some arguments between the spin alignment in the open cluster. They should not be, but anyway, is that so for all the cluster members, do they have the same spins in the same direction, or they are basically random? Right. So, well, there was a Nature paper in 2007 using astrocosmology saying that 70% of the 48 red giant stars in 2 quite old open clusters shows low inclination angles, so which support the yellow point here. But more recent study shows that they tend to have some systematic bias, and they favor the orange distribution here. Right? Yeah. Later, we also try to extend this a bit, but we need to know the period of the rotation of stars and Visa and I, which require Kepler and test observation, sometimes not so easy to acquire, etc., etc. However, these BE stars, recently Lally and Scout found out that the H alpha line profile of the BE stars is actually correlated to the inclination angle. So we can see that if it's face on, it's basically just one emission. But if we go to edge on, it is two emission, or like one huge emission with something inside. So we change with inclination angles. And using the method I present in my paper, we can see for now which stars is actually in emission in BE phase, which is short. And then so we can eventually, for example, for one of the clusters, NGC 663, we can capture different at least 13 OBA stars, and showing and looking at their H alpha lines. So this is what I have from one of my observations. But it seems that if we compare the line profile of the structure I shown here with this figure, it seems that we have like this is quite edge on, and to here is middle, and here is basically face on. So it's still a preliminary result, but the group of the spectra here basically shows that we will favor the conclusion that we actually don't have spin aligned clusters. Okay, 21 minutes. So the summary is that we have a new method to detect BE phenomena in WISE band more or less in the first time, so we don't need spectra anymore, more or less. We found more than 2,000 OBA stars showing BE phenomena in the WISE band in the last 10 years. They are redder, they are brighter, they show larger H alpha emission when they develop a depression disk. Yeah, most of the outbursts and decay phase are around 1 year, and if we have more infrared and optical photometry, or for example, the most observation or for most observation even, we may have a better constraint on the physical reason of triggering this BE phenomena eventually. But we are still not so clear about that, but we'll see. Okay, and that's all the content I want to share. Thank you.
Thank you very much. Questions for the speaker? Please.
Thank you, Nietzsche. So I have a curiosity. Do you observe any link correlation between the infrared excess and the spectral type or stellar properties, being temperature, masses, and which direction do they go eventually?
True. We do have something like that, but because most of them are OBA stars, right? So we would expect, I may have a figure here, but let's see if I do. Yeah, so neglect the group 2 stars. I think those are some weird thing here, but this is the most relevant figure, I think, between the stellar properties and the BE stars. So this is all the BET stars I found in the whole galaxy, and this is the distribution of the effective temperature from Gaia. I don't have a really good expression on that yet, but most of them are B-type stars, especially they are centered in B5, around 1.5 to the -4 Kelvin. So simply, we expect less stars in this side, more or less, because I would say their rotation is slower. They have a magnetic breakdown, etc., than in here. And I'm not so sure for what we should expect for the O-type side, maybe. But eventually we don't have so much OBA O-type stars in here, so the number, of course, goes down.
So if there is a correlation, that will mainly depend by the amount of mass that stars have in their accretion disk, if I understand correctly.
Probably, or also how eventually how fast the stars rotate.
Other questions? Yes.
I mean, thanks. Curiosity, you mentioned this sort of long timescale variability related to, I guess, outflows, each of these. Some of these stars are also showing variability related to pulsations, like slowly pulsating these stars. Is there any clear connection between the properties of their pulsations and these outbursts?
True. The short answer is that I hope yes. A bit longer answer that is this is something I haven't had time to touch about. The reason of the BE phenomena is not clear yet. Many previous studies think that there are some binary interaction, etc., etc. But recently, not so recently, NAIA 2020 actually showed that the pulsation of the massive stars may lead to BE phenomena. Is that there is one kind of specific ways inside the star that they can continuously move the angular momentum from the interior to the surface. And when you have too many angular momentum in the surface no longer becomes stable and they explode, form the BE phenomena, form the decretion disk, and the whole star back to this stable phase. So these things happen again and again. So there may be some connection between the BE phenomena and pulsation of the stars. Unfortunately, they predict for this particular stars, this event happens per 11 years, which is just the length of the whole WISE mission. So we are not so lucky to see if we have really, we can confirm this or not.
Okay. Other questions? If not, let's thank the speaker again.